h of x. I could use anything, but I'm going to use h of x. Sorry, the green, I know it doesn't come out very good. H of x equals 0. Those are my three functions that I'm dealing with in this problem, all right? I'll probably wind up drawing this again. Let's talk about area 1. Well, it's going to be an integral, right? I'm going to be adding up these rectangles. I'll draw the rectangle over here again for you so you have it. What was on top for area 1? Blue on top, green on the bottom. Okay, so what we need to know is what this height is right here. Well, that will be the top minus the bottom, right? Top minus bottom. What's the top one? Root x minus? Root x minus 0, right? Because the green one is 0. So root x minus 0, and then this is always dx, isn't it? So this is top minus bottom. And so this integral would just, I don't need the 0, do I? I just wrote it just so you understand it was top minus bottom. This is just root x dx, right? That's all it is. Now, you need numbers here, don't you? Yes. Okay, can you figure out what the numbers are? I think everyone can just visually see this number, right? 0. That's 0. How about this one? You got to set them equal, don't you? The red and the green, set them equal to each other. So what happens if you set this equal to this? So for the intersection, I set the red one equal to the green one, right? Are we having fun with colors today? I set the red one equal to the green one, right? That's what I'm trying to do, figure out where they hit each other. That's, you probably visually could have told me it was 2, right? That's okay, like on a test you don't have to set that up. You could just tell me it's 2. But if it's wrong, all right? So be careful. X is 2, right? X is 2. So 0 to 2, right? 0 to 2. All right, good. That's the area of 1. Now we do the same thing for the area of the second one. So for the area of 2, the second one, area 2, it'll be an integral. We'll figure out the limits of integration in a second. Now our rectangle looks like blue on top, red on bottom. Blue on top, red on bottom. So I have to do it on the side here. That's square root of x is the blue minus what? X minus, yeah, you know what, that sucks. Let me do it right here. It's square root of x minus 2. Is that right? Did I write that correctly? No, there's something wrong with the way I wrote that. I have to have the parentheses around that. I'm doing the top function minus the bottom function, right? Top minus bottom. You have to have the parentheses around the second function. If it has more than one term, that negative has to distribute through. Now, how wide is it? Dx. Okay, so what's the area of that? This times the dx, right? That's what goes right here. So I have root x minus x plus 2 dx. I went ahead and distributed now. I took this and passed it through. Do you have any questions on that? What else do I need? What's that? Intersection. Well, you know this is what? 2? Right? You just need to know this right here. We don't know what that is. So we have to set the blue and the red equal to each other. So we need the intersection. So I'm setting the blue and red equal to one another. The blue one is the root x. I'll do it this way. I'm setting root x equal to the red, which was x minus 2. Ooh, what kind of equation is that? Call that a square root equation or a radical equation. How do you solve radical equations? There's a whole set of steps I went over in my 1414 class a couple of weeks ago. First thing is you isolate the root, the radical. Okay, you get the radical by itself, which here it is already by itself. And now you like raise both sides of the equation to whatever power would kill off the radical, in this case squaring. We square this side, square that side. So we square this side, we get what? X. Careful. When you square that side, you don't get x squared minus 4. You don't get x squared plus 4. You get x squared minus 4x plus 4, because you have to square this, which means you have to FOIL it, right? FOIL it out, expand it. That times itself. Do that, you get this. Now you have a quadratic, right? Move everything over to one side. And hope that that factors, which it does. Minus 4 minus 1. We have two solutions, don't we? Yes. We have two answers. Which one is it? Which one is it? Well, remember, go ahead. It's 4 or 1, right? It's one of those. So remember when you're solving radical equations, back to college algebra, when you're solving these, when you square both sides of an equation, you introduce the possibility of what are called extraneous solutions, meaning one of these answers may not work, or they both may not work. We have to check them. So I need to check now I can tell from the picture what the answer is, okay? I can, but just going back to how we solve equations, I have to put 4 in here and check. Square root of 4? 2. 4 minus 2? 2. That checks, right? That works? Okay. 1. Square root of 1? 1. 1 minus 2? Negative 1. 1 doesn't equal negative 1. That's why that answer is not there, okay? So 4. This is 4. So I can put on I'm going back to my integral. I can go 2 to 4. The order in which you do this is not important. If you wanted to, you could have, before you found the formula for the rectangle, you could have found your points first if you wanted to. You could find your intersection, do all that first, then go find your integrals. There's nothing that says you have to do it in any particular order. You have to be able to come up with a formula for the area, and you have to be able to come up with your limits of integration. All right, so now we have two integrals to work out, don't we? Two integrals. Now, look, we're going to get to a point in this class where we're going to stop working the integrals out. All right, we're going to get to that, and we're going to be done. That's going to be that's where we stop in the class. Like, we won't take it any further just because of time, right? But since this is the second example, we're going to work this all out. So I have basically that my true area, the area is area 1 plus area 2, right? But that's just the integral from 0 to 2 of root x dx plus the integral from 2 to 4 of root x minus x plus 2 dx. You have to do these two integrals separately. You can't combine these integrals together. You can't, because this one goes from 0 to 2 and this one goes from 2 to 4. If they both went from 0 to 2, then you could put them together. But you can't because they have different limits of integration. All right, time for some antiderivatives. Okay, the antiderivative of the square root of x is 2/3 x to the 3/2. So I'm using the power rule on that, right? Evaluating that from 0 to 2. Plus, now over here, the antiderivative of that is 2/3 x to the 3/2 minus 1/2 x squared plus 2x, but that evaluated from 2 to 4. Okay, I don't feel like doing that computation, so I'm going to just use the computer to do it. All right? You all right with that? You understand what you have to do, right? Plug in numbers and all that. Okay, I'm just going to get to, what do y'all want to use? Alpha, Wolfram Alpha? I know a lot of y'all are using what, Symbolab these days? So I'm going to zoom in on this so you can see how I type this in. Right, it's 0 to 2. And then here, square root of x. And then next to it, I'm going to put plus, and then I'm going to do another integral. And this one's going to go from 2 to 4. And this one is, I'll do parentheses. Let's do square root of x minus x plus 2? Yes. Minus x plus 2, close parentheses. Make sure that that didn't go under the root. Yeah, okay. With respect to x, we're probably going to get an exact answer from the computer. In other words, it's going to give us like not a decimal. Yeah, look at it. Gave us like this. Oh no, here we go. Here's the result. Wow, 10/3. Wasn't expecting that. 10/3. 10/3 is the answer. On your exam, I'm probably going to ask you for the decimal because there's so many different ways that students might write this out and not cancel things out that if everyone goes to a decimal, we should all get the same answer. So 10/3 is our result. Okay, we good? All right, now I want to do that problem again. Let's do the problem again. And I'm going to introduce you to a different concept. So what we've been doing here, right? What we've been doing here is following this method right here. That if we have functions of x, right? If we have functions of x, then we're going to draw these vertical rectangles. We're going to come up with a formula. We're going to use the integral, right? However, in the problem we just did, y equals the square root of x, y equals x minus 2, and y equals 0, when we drew that region and we had this picture, this, when we had this picture, we saw that we had to break it up into two integrals, right? We had to break it up into two integrals. One that went from here to here, and then another one went from here. And it wasn't that bad, right? Like it wasn't like the end of the world. However, there's a similar approach to this if we have functions of y instead of functions of x. So what if we just imagine now we are looking at functions of y instead, and now we are going to use horizontal rectangles instead of vertical rectangles. So look at this picture here. All right, so do you agree that the red and the blue are functions of y? Because they pass the horizontal line test, right? So the red and the blue are functions of y. They are not functions of x, right? Well, the blue one's a function of x, isn't it? But the red one is not. The red one is not a function of x. But they're both functions of y. So what if I draw my rectangle horizontally instead of vertically, right? And now I try and find a formula for the area of that. Well, here's that rectangle right here. Here's that rectangle. Okay, how tall is it? Well, what I'm going to do is instead of moving left and right dx, right, I want to just move up and down. So this is going to be dy. Y is going to be my independent variable. So I'm going to move up and down, that's dy. And then I need to know how wide it is. And to find the width, it's the same thing I did when I was doing like top minus bottom, but we're turning it over and we're doing kind of like the right side minus the left side. And the right side would be this function f. So distance from here to here would be f of y. And then distance from here to here would be the g, that's this blue curve. That's g of y. And so that distance would be the difference of the two. So you'll see it's like the same thing, but we're just like turning sideways and looking at it that way, right? So the area of the region should be how long this rectangle is, which is f of y minus g of y, times the thickness of it, the height right there, dy. But now we're going to go from c to d. Where's c and what's d? It's not our left to right, right? We're not moving our rectangle this way. We're moving our rectangle up and down. So now I need to go from c, which is this point, all the way to d. Does that make sense that we could use that same method? Just kind of viewing everything sideways? So when you look at this, would there be an advantage to us if we rotated our heads and did that rectangle the other way? So like if we did a rectangle this way instead, is there any advantage over what we just did? What is it? You don't have to split it, right? Because where would these rectangles start? Down here, right? And then you'd move and get all these rectangles all the way up through here, right? You just move through with all these rectangles. And the whole time that you're getting the area of all these rectangles, what's the function on the right side? The red. And what's the function on the left side? The blue, and it never changes. Do you see that? That's probably better for us to not have to split it up into two integrals. So let's see if we can't set this up. I'm trying to find that area. I'm going to use horizontal rectangles, right? But what was kind of the catch with the horizontal? These have to be functions of what? Of y. Are the blue and red functions of y? Do they pass the horizontal line test? Does the blue one pass the horizontal line test? Does the red? Yes. Are they solved for, don't they have to be solved for x, not y? Can you solve these for x and y? Yes. I'm sorry, can you solve these for x? Let's take this, let's solve that for x. How would you solve that for x? Square both sides, and you get x is y squared. Could you solve this for x? Just add 2 to both sides. X is y plus 2. Now, you don't need to worry about solving this for x because that is just going to be what for us? Where we start our rectangles, right? At 0, and then where will we stop? Wherever we hit right here, right? Which we'll have to figure out in a moment. Okay. Let me color code this again. The red one was the line, right? This one. The blue one was this square root one. But now I've switched those, right? I've switched this to this. The red one is on the right, right? The red one is on the right. I like to call the one on the right f. You could have called it whatever you want. I'm going to call it this f of y equals y plus 2. See, this red one I'm looking at as a function of y now, not a function of x. And then the blue one right here, I'm going to call this one, since it's the one on the left, I'm going to call it g of y, and that one's going to be just y squared. Let's take a look at this rectangle. Okay, how tall is it? dy. That's the easy part. Now, how wide is it? It's the right side of the rectangle, which I didn't put here. The left side's the blue, the right side's the red, right? Like that. So you're going to take the one on the right, which is the red one, yes, f, and you're going to subtract from it g. So right minus left. So I'll put y plus 2, but then take away what? G of y, which is y squared. So this, what we're doing here is we're doing f of y minus g of y, or if you want, you could say it's the right end minus the left end. So instead of top minus bottom, it's right minus left. Questions or no? All right? Sure? So far, our integral looks like this. Y plus 2 minus y squared dy. And now we need our limits of integration, right? We need our limits. So we need where they hit each other. How do we find the intersection? We set the blue and the red equal to each other to find that, right? Here's the blue, here's the red. Set these equal. Y squared must equal y plus 2. That's a quadratic. See, it's a quadratic in terms of y, right? We're trying to solve for y, not x. So move everything over to one side. It factors. What do we get? Factor-wise, y minus 2, y plus 1 equals 0. You get two answers there. Y is 2, y is negative 1. Which one of those is the one? I think it's obvious from the picture, yeah? This got to be 2, right? It's got to be 2. Now, where are we going to start? Where do we start these rectangles? At 0, right? At y equals 0, we stop at 2. See, when we turn everything to the side, we're no longer letting our rectangles move left and right. We're making them move up and down. So we start at 0. We start making these rectangles, adding them up, and we stop when we get to y is 2. And what are those rectangles? These are this is the area of each one of them, right? That's the area of each rectangle. Goes from 0 to 2. Yeah? Yes?
So y equals 0 doesn't really matter, it just tells us where we start from the bottom.
Yeah, but that came from this right here. Remember, this right here was the green line. That's why I started at y equals 0. So yeah, that's only telling us where we're going to start. All right, let's do that integral. What should the answer be? If there's any justice in the world, this answer should be what? 10/3. Right? We shouldn't get two different answers, right? Just because we chose to do it a different way. Right? So the antiderivative of this is 1/2 y squared plus 2y minus 1/3 y cubed, evaluating from 0 to 2. I like this integral because I like plugging 0 in, right? 0 is going to kill everything, won't it? Okay, so when I plug in, I'm going to plug in 2, and then whatever I get when I plug in 0, well, I know I'm going to get 0 there because it's a big polynomial. Let's plug in 2. 2 into here. 4, half of 4 is 2. Plus 2 times 2 is 4. Minus 2 cubed is 8. This is minus 8/3. 8/3. This is 6 minus 8/3. Get a common denominator. 18/3 minus 8/3 is 10/3. I think that was much more efficient to do it that way. All right, so this idea of vertical rectangles, right, is when you have functions of x. Horizontal when you have functions of y, and sometimes you can do it both ways. And it's just a matter of what makes more sense, right? Like what's going to be more efficient. Ooh, this is always an interesting one. Because of the graph. Same sort of question. Here, find the region bounded by those things, find the area. So y equals sine x, y equals x, x equals pi over 2. What the hell? X equals pi over 2, and x equals pi? Yeah. Let's try and graph these, okay, one at a time. Y equals sine x. Let's do that one in blue. Look, you might wind up doing a graph and then starting over with your graph. Like you might draw it the first time, you're like, you know what, that graph sucks. Let me draw a different one. Okay, I'm just going to see how this goes. Sine x, right, I know that looks like this. Starts at 0, goes up, goes down, goes this way. It also goes the other way, right? It goes like that. Okay, that's what sine looks like. Goes up to 1, down to -1. That's my graph right here. And that blue. It's terrible. Okay, next one. Oh, y equals x. This one should be easy, huh? It's just the diagonal. Am I sure that that's what it looks like? I'm not 100% sure. I don't know if this line, okay, let me just keep going. X is pi over 2. Where's pi over 2? X, well, what is x equals pi over 2? What is that when I draw it? Vertical line, right? It's a vertical line. X is pi over 2. Where's pi over 2 here? Well, this is pi, right? Oh, I have pi there as well. So let me do that one. Pi, x is pi, that's this vertical line, right? That's x is pi. And I'm out of colors. X is pi over 2 is right here. Oh, shit. I don't know. My picture's not good enough. I don't know if I see a region bounded by all of those. Do y'all see that I have some limitations now on what I can do just with a quick sketch? So I think I'm going to need some sort of graphing utility to help me see what's happening here. All right? So yeah, I'm looking to see if there's an area where the red, blue, green, and black enclose a region. That's what I'm looking for. I need all 4 of those curves to be enclosing something. And yeah, don't trust my picture because I don't know how accurate it is. I just drew it by hand, right? So let's go to Desmos. Let's start a new one here. Okay, let's go. There's sine. Y equals x, there's my diagonal. X equals pi, and x equals pi over 2. All right, for us, the sign was blue, right? I'm even going to make it match what's up on the board. The other one was red. This one was black. And this one was, oh no, this one was black. Black and green. Okay, so there's what I have, right? We're going to have to zoom in to see this. So I'm going to zoom in. I'm going to stretch my x-axis out a little bit. Okay. I think I'm happy. I think I see it. I think I see that. Now Desmos made that pretty okay to see the region. Do y'all see the region bounded by all of them? It's this right here, right? It's this right here. You don't include this because this one is not bounded by this line, right? So it's this region right here. Now, let's see what our graphing calculator would have given us. All right, so I'm going to go to my graphing calculator and do the same thing. I got to turn it back on. It turns itself off. Isn't that weird? It's literally using the same ROM that the calculator uses. So it doesn't even know it's like working on a computer right now. All right, so I'm going to go here. I'm going to go up here and clear that out. I'm going to put sine x. And go ahead and hit enter. Then I'm going to do, what was it, y equals x, it's just x. Okay, now we have a problem. How do you graph vertical lines on a graphing calculator? Do you? It doesn't give you the ability to do it, right? It's not a built-in thing that's right here I can do horizontal lines. I can do y equals 5, it'll draw me a horizontal line up 5 or down 5, right? Or down wherever I want it. But I can't do verticals. So let me graph it right now to see what happens. I'm going to hit graph. I got to wait for it to do something. Okay, yeah, that sucked. I'm going to go zoom standard first just to make sure I have a standard window, see if that helped. Also, I need to check what mode I'm in. I'm in radian mode. Okay, good. Zoom. Let's zoom in. And I'm going to move my cursor. Can y'all see my cursor moving? I'm going to zoom in around right there, and I'm going to hit enter. See, but do you see the limitation here? We have a pretty major limitation. I don't know where pi is, and I don't know where pi over 2 is in that picture, do I? Don't. Okay, so let's do something. First thing I'm going to do is, let's just, so we don't get too far away, let's just go finish solving this problem using what Desmos gave us. Because Desmos, we know what to do now, right? I mean, at least I think we know what to do, yeah? Let's use Desmos, let's answer the question. Then I'm going to show you a way that we could have gotten this region on that calculator, right? Because I know that, yeah, we could all do this, but during a test, you need to be able to do that, right? So let's go over here. Let's draw this region out, and I'm going to use that picture. So we have the red here, we have the green, and the blue. So the blue is down here, like that. We've got the green right here, and we've got the black right here. All right, look at that region. We're trying to find the area of this right here. Would you like to do this with vertical rectangles or horizontal rectangles, and why? Horizontal? Anyone for vertical? Vertical? So look, if you're going to use horizontal rectangles, that means that you're going to start somewhere and move your way through, right? And while you're doing that, the function on the right should never change, and the function on the left should never change. But do you see it will? Like if you start down here, the function, like a little rectangle right in here, green on the right, blue on the left. But if I do a rectangle right here, it's what? Green on the right, black. And then when I get up here, it's what? Green and red. So you see if we do horizontal rectangles, we're going to have to do 3 separate integrals. 3 different kinds, 3 different setups. But if we do a vertical rectangle, right? Vertical instead, red on top, blue on the bottom, red on top, blue on the bottom, red, blue, no matter where I am, right? No matter where I am. So that's the way I want to go. Okay? So I need to do this, right? I've got red on top, blue on the bottom. Pardon me? Yeah, both of them work in this case, but one of them requires 3 integrals, the other one just requires 1. You could do it either way. Now, let me strike that for a second, hold on. You can do it either way. However, if you're going to do vertical rectangles, you have to be able to solve each of these for y, which they already are, aren't they? If you're going to use horizontal rectangles, you'll need 3 different integrals, and you have to be able to solve these for x. Can you solve that for x? Yes, but you'll bring in an arc sine, right? And then you solve that for x, well, it's already solved for x. So I would be concerned about that arc sine because you're going to have to integrate that arc sine, and then that's going to be, well, what's the antiderivative of arc sine of x? The antiderivative, that's integration by parts. That's a mess. Yes?